Dear students, welcome to EPG Pathshala. This module completely randomized design 2 is in continuation of the previous module, completely randomized design 1. In that module we already discussed that what is ANOVA, construction of the completely randomized design and estimation of the parameters and total variation that is separated into different components. In this module we will discuss that how to check the validity of the parameters, or you can say how to test the validity of the assumptions in the model. After that we will discuss how to apply the post hoc analysis. Post hoc analysis means when we have our null hypothesis rejected, then how we proceed further. So in this module we will discuss all these things in very depth or detail. Let's get started. We will discuss some other topics like checking the adequacy of the model, test for the equality of the variance, post hoc analysis, comparison of two treatments using different parametric test, confidence interval of the parameter, and some introduction to random effect model. This model will help you to understand that before applying ANOVA, how we have to check for the validity of the assumption. It is also essential to know how to proceed further if our null hypothesis will be rejected. For that, testing of pair of treatment population mean parametric as well construction of the confidence interval for difference of the mean of pair of treatments will be discussed. Some examples will be discussed in the manner for better understanding. We have already covered the topic of completely randomized design with complete derivation starting from the building of the model, defining the null and alternative hypothesis, method of least square to estimate the parameters of the model, including the variance sigma square with the construction of ANOVA table, and how to derive the values for the different sum of square in the module completely randomized design. In this module we will discuss about the adequacy of the assumptions, as one can only apply any model on the data if the data satisfies some assumptions. So this model will consider the method that are available in the literature to test these assumptions. There are many methods that are available in the literature. We will discuss some of the most important methods here only. We will discuss about the confidence interval of the parameters as well as the comparison of two treatments when our null hypothesis is rejected. So first is how to check the adequacy of the model. We will discuss about the validity of the assumption before applying the ANOVA. We have to check the assumption of the normality of the error term. There are methods like histogram, dot plot, line chart, QQ plot, cumulative frequency plot, and through KS test, that is Kolmogorov-Smirnov test, WS test, Shapiro-Wills test, Jarque-Bera test, and D'Agostino test. One can determine the normality of the error term. Graphical representation will not be the exact method to check about the normality of the data. If the value seems like normally distributed but are not actually normal. Graphical methods are not very useful when the sample size is very small. Then the histogram of the data does not look normal, but in reality it may follow normal distribution. Statistical tests give more actual probabilities about the normality of the data. In the testing of the hypothesis, we want to test about whether the data was drawn from the normal population or not. The hypothesis to test about the normality of the data are null hypothesis. The sample data are taken from the normal distribution, or the sample data are not significantly different from the normal population. An alternative hypothesis is the sample data are not from the normal distribution or the sample data are significantly different from the normal distribution. There is a difference in testing of the hypothesis than others, where our main motive is to estimate about the difference in mean median and variance of the data. In this type of hypothesis of differences, our interest is to reject the null hypothesis if the probability value, that is p value, of these events is coming out to be less than 5%, then we reject the null hypothesis. Here in the testing of the normality of data, our main interest is to see our p value to be greater than 5%, or so that we can accept the null hypothesis. So a probability value that is coming to be greater than 0.05, then it means that the data follow normal distribution, otherwise the data are significantly different from the normal distribution. And that assumption is assumed, and we assume that our data follow normal distribution when the sample size is more than 30. As the sample size increases, it is assumed by the center limit theorem the data follow normal distribution on approximate basis. So for very large data set, the testing for the normality of the data becomes less important. Also, it is generally assumed that the data follow normal distribution when the sample size is more than 30. So first test is W/S test for normality. This test is very simple test that requires only the standard deviation and the range of the data. The test statistics is defined as Q is equal to R upon S, where Q is the test statistics, R is the range of the data, and S is the standard deviation. Steps for applying this statistics is given here. First, evaluate the standard deviation of the data, and which is square root of the variance. Second, find the range of the data, that is highest value of the data set minus lowest value of the data set, and it is derived by using the formula H minus L. After that, evaluate the proportion Q is equal to R upon S. Now W/S test uses a critical value to test the hypothesis. If the calculated value of the test statistics falls within the critical value given in the table of W/S test, then we accept our null hypothesis and do not reject our null hypothesis. If the calculated value falls outside the range, then reject our null hypothesis. Sometime we are interested to find out the p value of the test statistics. Then if W/S statistics, that is Q is greater than 0.05, then the data are not significantly different from normal distribution. Jarque-Bera test, a test that has similarity with the goodness of fit test. Here sample data have been tested whether skewness and kurtosis of the data match with the normal distribution, and we have the test statistics given here as JB, which is equal to n into k3 square divided by 6 and k4 square whole square divided by 24, and where k3 is equal to summation over yi minus y bar whole power cube divided by ns square, and k4 is summation is over yi minus y bar whole power 4 divided by ns4 minus 3, where yi is the ith observation of the sample data, n is the sample size, s is the standard deviation, k3 is the skewness data, and k4 is the kurtosis of the data. The value of the JB test statistics is compared with the chi-square distribution table with 2 degree of freedom. If the calculated value of JB is greater than chi-square distribution with 2 degree of freedom at 5% level of significance, then it means that the data is significantly different from the normal distribution and our null hypothesis is rejected. On the other hand, if JB is less than chi-square distribution, that is tabulated value, with 2 degree of freedom at 5% level of significance, then we do not reject the null hypothesis and the data are normally distributed. The another test statistics is D'Agostino test. This test is considered a very powerful test to detect the departure of the data from normality. It is based on the D statistics, which gives an upper and lower critical value. The test statistics is defined as D is equal to T upon square root of n cube SST, where SST is the sum of square of total, where T is equal to summation upon I, which is I minus n plus 1 upon 2 into yi D is the test statistic, SST is the total sum of square of the observation, and N is the sample size, and I is the order or rank of the YI observation. And there are few steps for evaluating the value. The first step is, first order the data in ascending order or decreasing order. Calculate the value of t by taking the difference of the ith observation rank with n plus 1 upon 2 and multiply with yi and take summation. Calculate the total sum of square, that is subtracting each observation from the mean value of the data and square it. Now take the sum of all values. Now put all the values in the expression of d. Now compare the d value with the D'Agostino normality test table. Now another test is Kolmogorov-Smirnov test. Kolmogorov-Smirnov is another test for normality. It is also known as KS test in the literature. The test statistic is defined as Dn is equal to f expected value of y minus f observed value of y and take mod and take maximum value of the mod, where fy is the cumulative distribution function of the random variable y for the observation yi where I vary from 1 to n. F observed value of y, which is equal to number of observations below y divided by number of observations. If we order the observations y1, y2 and yn, then observed value of f is valued as I upon n. Hence, first calculate the difference of observed cumulative distribution function from the observed distribution function and choose the maximum among them. This maximum value is the value of the test statistics. Now we have to compare the value of test statistics with the tabulatory value of KS table. If the value of the Dn is more than the tabulatory value for given n, then reject the null hypothesis, otherwise do not reject the null hypothesis. There is a note here. For large sample data set, the critical value must not be able in the data. For large sample data sets, set, the critical value may not be available in the table. So there is a formula to approximate out the critical value at 5% level of significance. It is given as D with 0.05, which is equal to 1.36 divided by square root of n, where n is the sample size. Now the question is, which test we should use to test normality. To answer this question, we discuss here the features of the different tests, and for W/S test, it is considered as the simplest test among all the tests. It also has some drawbacks, that it is not available in the statistical softwares like SPSS. Jarque-Bera, this test statistics basically used to test the normality through skewness and kurtosis, and it is very effective. D'Agostino, it is most powerful among all the tests, and another is Kolmogorov-Smirnov. This test is generally used in the practice, and this test is not sensitive to problem in the tail. This test is only give more appropriate result when the sample size is greater than 50. This test statistics generally available in statistical software. So there is a note here. As we discuss about the validity of the assumption and how to verify them, but if the data are not from the normal distribution, then what is the problem? As we already discussed that our results are only valid if our data meets some assumptions. As error are not follow normal distribution, then it may lead to serious consequences for the experimenter to make any statement about the problem. So first, now we have to discuss how to test the equality of the variance. The most widely tested statistics that is used to test about the equality of the variance is Bartlett's test. The null hypothesis given here as H naught, which is equal to sigma 1 square is equal to sigma 2 square and so on, is equal to sigma p square. And alternative is at least one variance is different. So the test statistics is defined as chi-square of calculated value, which is coming out to be 2.3026 into q upon c, where q is equal to np minus p into log of 10 sp square minus summation n minus 1 log of 10 si square, where I vary from 1 to p, and c is equal to 1 plus 1 upon 3 p minus 1 into summation I vary from 1 to p n minus 1 minus np minus 1 power minus 1. So sp square, which is equal to I is equal to 1 to p n minus 1 si square upon np minus p. For a given sample, we can calculate the value of chi square of observed value. We should reject the null hypothesis for the large value of chi square with observed value, that is chi square of observed value is greater than chi square a alpha p minus 1, where chi square alpha p minus 1 is the upper alpha percent point of the chi square distribution with p minus 1 degree of freedom. We can also compute the p value to make decision about the null hypothesis. Now, for the testing the treatment means using least square method. So this technique we discuss how we can test the treatment means whenever a null hypothesis for ANOVA table is rejected. So when we reject our null hypothesis of the ANOVA table for the testing of the treatment means of more than two groups, the next step is to find out the pairs of the treatment that are not significantly different, or to establish the ordering among the treatment means. So if there is any significant difference between the treatment means, we can take two pairs at a time to compare the treatment means between them to see which pairs are not statistically significant, so that we can put them in the same group and which group are statistically significant, so that order them according to their mean. The steps are given below. Let us suppose we have p is equal to 4 treatments. First find the treatment mean and arrange them in ascending or descending order, as y2 y3 dot is less than y2 dot bar less than and so on y4 dot. In the next step we have to examine about the treatment mean through testing by taking two pairs at a time. We know that for the testing of mean of two groups with unknown variance, t-test is used under the assumption of equal variance. Our hypotheses are given here as h naught, which is equal to mu2 is equal to mu1, and alternative is mu2 is not equal to mu1. So in the above hypothesis we carried out two-sided test of the hypothesis. That means we are interested in to check whether our second treatment mean is significantly greater than or less than the first treatment mean in both direction. It would be observed from step 1 that we already arrange the treatment mean in ordering. So if you have any idea about the means of two treatments, then we can modify our hypothesis as follows: h naught, which is mu2 is equal to mu1, and h1 is mu2 is less than mu1. In this case the test statistic is called one-sided test. In general, the test statistics for the two sample problem when variance is unknown is defined as y1 bar minus y2 bar minus mu1 minus mu2 divided by s into square root of 1 upon n1 plus n2, and that follow t distribution with n1 plus n2 minus 2, where yi bar is where I takes value 1 to 2 are the sample mean for the first and the second sample, and ni is the sample size of the for the ith population, s is the pooled variance of the both population, mu I is the mean parameter of the ith population. Here sigma square hat square, which is equal to sum of square of error divided by n minus p, is an unbiased estimator of the population parameter sigma square. Then the test statistic is given as y1 dot bar minus y2 dot bar minus mu1 minus mu2 upon sigma hat into 1 upon n1 plus n2, that follow t distribution with n minus p degree of freedom. Here h naught, the test statistic is given here as y1 dot bar minus y2 dot divided by sigma square sigma hat into 1 upon n1 plus 1 upon n2. Since it is two-sided test from the first hypothesis, so if there is any significant difference between the mean, then the test statistics must be greater than the upper 2.5% critical value of the t distribution. So which is y1 dot bar minus y2 dot bar divided by sigma hat into 1 upon n1 plus n2, which is greater than t value with n minus p degree of freedom at 0.025%, 0.025 level of significance. For arranging the statistics, we get y1 dot bar minus y2 dot bar, which is greater than t with 0.025 with n minus 1 n minus p degree of freedom into sigma hat into 1 upon n1 plus n1 upon n2. The value on the right hand side of the expression is termed as the least square difference. That is the value that the difference between the treatment means are more than this quantity. Then we can say that there is a significant difference among the treatments. Also, if we have same sample size for all treatment, then the least square difference will be same for all treatments. Then the easiest way to test about the treatment means of any pair is that if the difference between the pairs of treatment mean is more than the least significant difference, then we can say directly that pairs of treatments are significantly different. Let us suppose 5% level of significance. We want to calculate the least significant difference between y1 dot bar and y2 dot bar. The formula is t into sigma hat into 1 upon n1 plus 1 upon n2 whole power 1 upon 2, where t is equal to t with level of significance 0.025 and with n minus p degree of freedom. That is the value of the t distribution with n minus p degree of freedom at 2.5% level of significance. If the difference of two treatment mean is y1 dot bar minus y2 dot bar is less than the significant difference value, then we can say that the treatment means of this pair fall into the same category or group. We can make a symbol for them. We can repeat this process for other treatment pair and for y1 dot bar and y2 y3 dot bar and so on. So here we have example. A random sample of marks out of 50 students scored in the mid-semester examination in statistics from environmental sciences, biostatistics and human genetics department from Central University of Punjab were taken respectively. The results were given here as now we already discussed this example in our previous module. So from the previous module we already have the values that y1 dot is which is equal to 320, y2 dot which is equal to 225, y3 dot which is 335 and y double dot is equal to 880, n1 is equal to 10, n2 is equal to 8, n3 is equal to 9 and double summation yi j square which is equal to 3052 and sum of square of total which is equal to 30152 minus 880 square upon 27 and which is equal to 1470.52. So sum of square treatment which is coming out to be 356.09 and sum of square of error which is equal to 1470.52 minus 356.09. So sum of square error which is equal to 1114.43. So sigma square hat which is equal to sum of square of error divided by n minus p, which is coming up to be 46.43. So in this example we have from the data we can observe that y2 dot bar which is less than y1 dot bar which is less than y3 dot bar. For a 5% level of significance, the least square difference between y1 dot bar and y2 dot bar is by putting the values in the formula we get the result as 6.67. That can be derived by multiplying 2.064 into square root of 46.43 into 1 upon 10 plus 1 upon 8 whole power 1 upon 2. The value of t at 24 degree of freedom at 2.5% level of significance can be derived from the table which is 2.064 and y1 dot bar minus y2 dot bar which is equal to 3.9. So y2 dot bar less than y1 dot bar, so both lie in the same group. For y3 dot bar and y1 dot bar, the least square difference is 6.46 and y3 dot bar minus y1 dot bar which is equal to 5.2. So here the treatment 1 and treatment 2 are not statistically significant different. Also treatment 1 and treatment 3 are not statistically significant different, but there is a significant difference between treatment 2 and 3, so we cannot combine them into the same category. To find out the least square difference between treatment 1 and treatment 3, the formula is given here as 2.064 into square root of 46.43 into 1 upon 9 plus 1 upon 10 whole power 1 upon 2, which is equal to 6.46. To prove that the treatment 2 and treatment 3 are significantly different, we find out their mean, that is 2.06 into 46.43, which is into 1 upon 8 plus 1 upon 9 whole power 1 upon 2, which is equal to 6.83. Now calculate the difference of treatment 2 and treatment 3, which is given as y3 dot bar minus y2 dot bar, which is equal to 37.2 minus 28.12, which is equal to 9.10. Since this difference is greater than the least square difference, this means that there is a significant difference between treatment 2 and treatment 3. This is the reason that our null hypothesis is rejected in the completely randomized design model. The other way to understand the difference among the treatment 2 and treatment 3 is through confidence interval. So in this section we discuss how we can find out the confidence interval for the difference of treatment mean. Our main interest is to find the confidence interval of difference of treatment mean. The theory of confidence interval and related stuff were already discussed in our earlier module. The confidence interval for the difference between treatment mean data from normal distribution is based on the test statistics for the testing of mean of pair of treatments. A 95% confidence interval for the difference of the population parameter, that is mu2 minus mu3, is derived from the form of the test statistics and is given by mu3 dot bar minus mu2 dot bar plus minus t with 2.5% level of significance and with n minus p degree of freedom into sigma hat into 1 upon n 3 plus 1 upon n2 whole power 1 upon 2. So if the confidence interval contain the term 0, that means there is a no significant difference between the term between the treatment means. But if the interval does not have 0 term, then the treatment mean are significantly different. To prove this thing, we continue our previous sample where treatment 3 and treatment 2 are significantly different. Now put the values in the above formula of confidence interval. So we have the values as 37.2 minus 28.1 plus minus 2.064 square root of 46.43 into 1 upon 9 plus 1 upon 8 whole power 1 upon 2, that is 9.1 plus minus 6.8, that is 2.3 and 15.9. So we have the interval given here as 2.3 and 15.9. Hence the interval does not contain the term 0. In the end, I would like to conclude that in this module we first discussed about how to test the assumptions of the model. In the first assumption, we discussed how to test the normality of the data. After that, we discussed that how to test the equality of the variance. That for that we use Bartlett test. For the equality of normality, we have different tests like KS test, W oblique S test, JB test, and so on. After that, we discussed what is post hoc analysis. In this, we discussed that if our null hypothesis was rejected in CRD model, then how we proceed further. For that, we use LSD test for the testing or treatment of two sample, and we can also use confidence interval for the testing of treatment of two sample.